In this video, I'm going to be talking about something called electron configuration. And the focus of this video is basically how to write electron configuration and some rules and principles that must be observed when doing so. So to start off with, the definition of electron configuration is it's basically organizing electrons according to their quantized energy level. So I can write that down. Organizing electrons according to their quantized energy level. So organizing electrons according to their quantized energy level. And you use quantum numbers to do this. Use quantum numbers, which was talked about in the last video. So we're seeing the importance of quantum numbers already. So before we get into how to write electron configurations, we have to first talk about a few principles / rules. So the first one we have is something called the Offbow Principle. The Offbow Principle basically says the order of filling orbitals with electrons is done from the lowest energy. So I'll just say lowest E to the highest E. So you fill these electron orbitals from the lowest energy level to the highest energy level. So I can write that down here, or I can just say a notation, filling orbitals with electrons. So what would that look like visually? So in the next video, I'll be showing energy or orbital level diagrams, but in this video, I'm just going to show how to write. But if just to sort of visually explain this, if we had, let's say, some energy level like this. So this would be the lower one. This would be the higher one. So when you're filling these electrons, you wouldn't just put them in the higher one, right? You would put them in the lower one first, and then you move on to the higher one. So that's basically the idea. You're filling orbitals with electrons from the lowest energy level to the highest energy level. Think of it like filling a glass of water. You start from the bottom and then you make your way to the top. Sort of like that song. The next one we have is, I'll do the Pauli exclusion principle. So the Pauli exclusion principle basically says orbitals can contain a maximum of 2 electrons and each must have an opposite spin. So an orbital looks like this when you draw an orbital energy level diagram, and it's basically just a line. And it says basically they can occupy a maximum of 2 and must have an opposite spin. So this little notation here, these like weird half arrows, this represents the electron. And if you recall from the last video, the last quantum number, the magnetic spin quantum number, indicates either it's plus up or plus minus half down, right? So in this case, we can see this is plus half up, and this is minus half, aka down. So that's the Pauli exclusion principle. In every orbital, there's a maximum of 2 electrons, and each must have an opposite spin. So max 2e, each must have opposite spin. Finally, we have Hund's rule. Hund's rule basically says when you're filling up orbitals in the same energy level, you must fill all orbitals with single electrons before you fill an entire orbital. So what does that mean? So again, if orbitals are like at least in the orbital energy diagram, which I'll show in the next video, but I'm sort of showing it to you now. When we're filling these electrons up, we're not gonna do like this. Like let's say we had 4 electrons, right? This is what you're not supposed to do. This is wrong. What you're supposed to do is fill every one up one at a time and then give that one. So this is correct, this is wrong. And the reason is we do this to minimize E repulsion or electron repulsion. because like charges repel, right? So it wouldn't make sense to straight from the get-go to put, you know, all these electrons right close to each other when you can sort of space them out. So it's this whole idea of spacing them out. So this is correct. I should circle this in green, and this is wrong when you have 4 electrons. So basically, you know, those are the sort of rules, and that's pretty much it. Now we get into the fun. So here I have my periodic table. You'll notice I've done something weird with it. I've colored it up. So remember the orbital shape quantum number I talked about, aka L, which dictates SPDF? That's the whole idea here. So the periodic table can be split up into these SPDF blocks to describe their energy level. So we have on the left here these alkaline earth metals as S, and also hydrogen and helium are included. Helium is here, but really it's just supposed to be here in the S block. You can search up periodic table electron configuration and it'll show you something like this. And then the P block, we have all these gases / metalloids. The D block, you have all the transition metal. F block, you have the sort of unstable stuff going on like uranium and whatnot. So yeah, that's basically it. That is the SPDF, you know, periodic table. And the way you write electron configurations is you follow this order. You go from left to right and then up till down, or in other words, diagonally across, as I've shown here. So how do you write it? So basically the first step is you write, the first thing you write is the principal quantum number, aka the row it is in. So these 1, 2, 3, 4, 5, 6, 7, these rows are just n. That's just the principal quantum number or the period number. That's basically it. You write that, so that would either be 1 to 7, and then the next thing you write would be the orbital shape quantum number. So I'm going to represent it by L, and that's either S, P, D, or F. And then finally, so this is to indicate which block it is in. The N would indicate which row it is in. And finally, you put a little exponent in. In this exponent, you're going to put the amount of electrons in that particular orbital. So this would be number of electrons in that orbital. So let's look at an example of this. So let's say we had hydrogen. If you look on our periodic table, that's the very first element. So if we look at its, let's start off with its principal quantum number, or the row number. That's just going to be 1, right? I can write that a little bit more straight. 1, there we go. And then the next thing we're looking for is we're just putting it right next to it. It's sort of like as if we're writing some, you know, math expression like this, right? They're all together. It's sort of like that. The next thing we're going to write is the block it's in. So we can see that hydrogen belongs in this yellow S block. So we put this S here to indicate it's in the S block, and then we indicate how many electrons are in that orbital. Within that specific orbital, they're just 1. Let's do another example. Let's say helium. Helium is, you know, I've indicated here. It's in the S block still, so it's 1. It's the same thing. It's in the same row. It's in the same block. But how many electrons does it have? Pause the video and think about it. So, if hydrogen has 1 electron, and if you remember from grade 9 chemistry the idea of valence electrons, it's sort of similar here. The very last, when you write these long electron configurations, the very last one will show you the valence electrons that are present. But basically, when we're thinking about for helium, is that, well, if hydrogen has 1 valence electron, then helium has 2 valence electrons, right? Because it has a full octet like these gases over here. So we would put 1s2. So that's basically it, because the visual representation would look like this. And then hydrogen is just like that, 1. How about let's try lithium. So lithium is in the second period, right over here. So we write 2. We know it's still in the S block, S. And then how many electrons? Think how many valence electrons does lithium have? 1. Oh my god. I'm so sorry. I made a mistake. I forgot to mention something. That was actually wrong. So with electron configuration, what you're doing is also you're counting. So when you approach something like lithium, actually, you have to include the previous row. When you start a new row, you have to include the previous row. And the way you can include the previous row is include the previous electron configuration or configurations. So when we're doing lithium, we would actually have to include 1s2 from helium to indicate we're moving on to the next period, and now we're going to state lithium. And so the reason we didn't do that for hydrogen, the reason for helium, the reason we didn't do 1s1, 1s2 is because 1s and 1s are remaining the same. The only difference is the number of electrons. So we can just write that as 1s2. But when we're changing the period or changing a block, so when we're changing the period or changing the block, then we have to include the previous number. So lithium would be 1s2, and then we know it's in the second period. We know it's still in the s block, and it has a valence electron of 1. So 1s2, 2s1. So that's basically it. You include the previous electron configuration or configuration like numbers based on if it's changed the period or if it's changed the block. Let's say we did beryllium now. Beryllium is right next to lithium. Pause the video and see if you can figure it out. All right, so beryllium is right next to lithium, right? So let's first start off with what we are going to write, which is 1s2, because again, we have to include the previous row's electron configuration. And now we know it's in the second period, we know it's in the s block, but what's going to be put for the little exponent? How many electrons? Well, it's going to be 2, right? Because we know the final, when you write series and series, let's say you have 1s2, 2s2, 2p, let's say 5. This sort of represents the amount of electrons it has currently and how many it can either gain or lose. So we know that beryllium is a cation that has a 2+ charge, and it can lose that, right? And we see that in here because again, in its orbital for 2s2, it would look like this, whereas 1s1 looks like that, 1s, 2s. So that's beryllium. Let's say now we had, let's say we did boron. So we would have to write, so boron is right here. It's in the second row, so we have to write the previous row stuff. So 1s2, and then we have to write the s block stuff. So 2s2, because we're just counting, we're sort of like tracking our steps basically. And now we're moving on to the p block. So it's in the second row, it's in the p block, and we put 1 electron. And the way to think about actually these electrons is to sort of count it. So in the p block, there's 1, 2, 3, 4, 5, 6. In the s block, there's 1, 2. In the d block, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. See what I mean? So we're going to see this with the p block stuff just right now. This 2p exponent number is going to go from 1 till, like it can range from 1 to 6 depending on where it is. So it's just like counting. That's all we're doing. Let's say we did carbon. Carbon is right after boron. So again, it's going to have 1s2, the previous stuff, 2s2, just counting, 2p, and since it's right after carbon, if it's right after boron, if boron is 2p1, this would be 2p2. Let's try fluorine. Fluorine is right before being neon. So it's in that same row, but we have to write the first stuff. So 1s2, 2s2, 2p, let's count. 1, 2, 3, let me just rewrite. 1, 2, 3, 4, 5. So we write 2p, 5. And this makes sense because we know that from our previous studies in chemistry, we know that fluorine just needs to gain 1 more electron to have a stable octet. And this is representing how many electrons it already has. It has 5 electrons. It just needs 1 electron to get a stable configuration. which would be 6. Now let's write for neon. So again, looking at the periodic table, neon is right after fluorine, so we know that we have to write the previous stuff. So 1s2, 2s2, 2p6, because neon has a full octet. All right, let's do some examples for writing electron configurations for periods 3 and 4. Let's say I asked for magnesium. Pause the video and see if you can figure it out. Okay, so this one's is gonna get a little long. We basically have to write all the things before it, right? Because we have changed not only the period number, but we have changed the block. So we have to include all the previous stuff before. So we're gonna have to write 1s2 to account for the first row, 2s2 to account for the second row, the s block, and then 2p6 because we're going all the way like this. We're basically making steps. So dot, 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 till we get to magnesium. I'm just gonna hit the undo button. There we go. So that's the idea. So 1s2, 2s2, 2p6, right? Because we're going all across that second row of the p block. And then 3s, we go past sodium and we land on magnesium, which is 3s2. Let's try sulfur. Sulfur is right here. Pause the video and see if you can figure this out. So with sulfur, basically we can just do a little hack right now. We know it's in the same row as magnesium, so we can just copy down magnesium's electron configuration first. 1s2, 2s2, 2p6, 3s2, 3p, because now we're in the p block, and let's count for sulfur. 1, 2, 3, 4. 3p4. So you'll notice it's getting a little longer and a little bit messier. And it's going to get really messy when we do the next part. So I'm going to teach you something different now. There is something called abbreviated electron configuration notation, or whatever the exact terminology is, but it's just abbreviation. And what you do is you're looking at, let me just erase this. You're basically sort of shortening what you have to write. So instead of writing all these things when you have to skip a period, you can just include the last noble gas you passed. So let's say for magnesium, right? Magnesium is right here. It's in the third period. The previous noble gas it just passed is neon, right? Because neon is in the second period. So for magnesium, you can write it as neon, bracket, right? And now it's in the third. Now we're moving on to the third block, 3s2. And we're done. See the difference? To start writing 1s2, 2s2, 2p6, 3s2. We can literally just write neon, 3s2. We can try that with sulfur as well. The noble gas that comes before it, right? So it's not about what it's close to, right? We wouldn't use argon. That's incorrect. Because we're in this notation, we're writing the gas that was before the certain element we're trying to describe. So we would write neon again, because sulfur is in the same period as magnesium. Neon, and then we can just write 3s2, 3p4, because 1, 2, 3, 4 for the p block. And that's it. So this is abbreviated electron configuration notation. Yeah. And then let's say we did, so let's move on to another. Let's say we did scandium. So scandium is right here. So pause the video and see if you can figure it out. So for scandium, I think I will just keep it abbreviated, just for the sake of this video. So for scandium, so scandium's in the fourth period. Now before scandium is argon, so we'd write argon in brackets, and then we'd write 4s2, and then here's where things get a little tricky, 3d1. Now, why did I write 3 for the d orbital when it's clearly in the fourth period? Think about it. So the reason for this is because not only of how the periodic table is arranged, but also because we write electron configuration in a way that represents lowest energy from the left. So when you're writing electron configuration, so E configuration, when you're writing this stuff, you always write, when you're writing your blah, 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 you're always starting from the lowest to the highest energy. So the last set of numbers and letters, that will be the highest energy for that particular element. So a 3D orbital is actually slightly higher than a 4s orbital in terms of energy. So this is a 3D orbital. If we had a bunch, because 3D, remember from last video, 3D can have 5 orientations, whereas 4s just has 1, right? And then yeah, so this is 4s, this would be 3D. It's just slightly above it. And that's just the nature of 3D orbitals. They tend to be higher in energy, just slightly. So the reason I've put 3D1 is because the way the periodic table is arranged, and also because how 3D orbitals have slightly more energy. So there's a certain pattern to know, and I'll write this down. I can write it down here, I guess, in white. So for every value for n, so s equals to n, right? P equals to n, right? These are the orbital shaped quantum numbers. They equal to like that value. And then d equals to n minus 1. And then f equals to n minus 2. This is a little pattern. And you can memorize when you're writing electron configurations. So when you move on to the 4th period, so when you move on to the 4th row, you're actually going to put a principal quantum number of 3 for that. That's just another like sort of rule you can follow. So yeah, so that's basically it. So that's why transition metals will actually be 1 less for every period they are, and then the F, there'll be 2 less for whatever it is. Let's say we did bromine. Another example, bromine. Bromine is right here. We know bromine is in the 4th orbital. Sorry, in the 4th period. So we can write the abbreviated notation again. So the gas that was before it was argon. So I'm going to put argon in here again. And then I'm going to write 4s2. Now remember how I counted all across the d orbital, and it happened to be 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we're going to have to write that all. So it'd be 3d10, because we're all moving past that. We're counting our steps. Then just 1, 2, 3, 4, 5. So this would be 4p5. And this is the way we write things. Don't ever, I know this periodic table shows it, but don't write these in numerical order. Don't put it like 3d, 10, 4s2, 4p5. That's wrong, because you're no longer writing it in terms of least energy to highest energy as you continue writing. So it's not technically correct. I know a lot of sources will show that, but you should try to leave it as 4s2, 3d10, 4p5. Like just leave it in terms of the order of energy, unless your teacher prefers it in that specific way. But from what I learned, you have to write it in this method. So that was bromine. Now let's move on to some really weird ones. Cerium. So where is cerium? Cerium is in the F block, right over here, first one. So I'm going to do abbreviated notation again, but let's take a close look at the periodic table, because the F block can be a little tricky. So the proton number for it is 58, right? And this over here is 57, even though you can't see it because I got cut with the markings, but that's 57, right? So we know cerium is actually in, the 6th row. So we look closely. Okay, it's in the 6th row. Let's look for the 5th row noble gas. Okay, that's xenon. So we'd write Xe in those brackets. X, oh, not how you write it. Xe. And then we write everything else. So Xe now, so that was the 5th energy. Now moving on to the 6th. So that would be 6s2. And now pause the video and see if you can figure out what would be right after this. So in order to reach the cerium, we first have to go through the D block, right? So the D block right over here, that's this La, lanthium, that's 57. And remember the pattern I said? For D, it's N minus 1. So instead of this being 6D1, it would be 5D1. 5D1. And then the other number that would follow it is now we're moving on to the F block. And in the F block, you subtract it by 2. Right? So this would be, so it's the sixth one, that's N. N equals to 6 here. But in this case, F would equal to 4. Because 6 minus 2 is 4. So you put 4F1. So 6s2, 5d1, 4f1. That is cerium. That's how you do it. Again, you can look at the periodic table and see for yourself. We first took xenon over here, moved on to the next row. Then we made a nice stop in the D block, and then we moved on to the F block. Let's try. Let's do uranium. So where is uranium? Uranium is right here. Pause the video and see if you can figure this out. So with uranium, let's sort of look at this number. So it's 92 in the periodic table. So we're gonna write it in, in the abbreviated notation to, save some time. So the following, the preceding noble gas would be radon, because if we look 86, because if you see, so the radon over here is 86, then francium becomes 87, radium becomes 88, 89, and then suddenly from 89 it makes a jump to 104. So we have to look over here. So we see 90, 91, 92. So we know that it has to be radon. So we put radon. So what's the symbol for radon? Rn. Yeah, Rn in brackets. And then we just look over here. So radon was in the 6th, so we're now moving on to the 7th row. So this would be 7s2. Then we make a brief stop on the D block. So this would be 61. And then now we're moving on to the F block, and this would just be 1, 2, 3, right? Because 89, 90, 91, 92. But we know that block is subtracted by 2 when you write it for the principal quantum number. So if this was 7, then this would be 5f3. So 7s2, 61, 5f3. Yikes, this looks very weird, but that's what it is. And I think you sort of get the gist. I think I'm going to stop the video right here. Maybe in the next video I'll quickly take up. Try mercury and lead on your own. So pull up your own periodic table. Don't look at one with its own electron configuration. Try to find one. And in the next video I'll take these two up. And then I'll also explain how to draw energy level diagrams. But yeah, that's pretty much it.